much for being here. Bueno, el título de su presentación es Ganando la batalla contra las malezas acuáticas, del control biológico clásico al control biológico aumentativo. Gracias.
Hola, estoy enferma, no hablo español. Okay, so I apologize. I'm not feeling. My voice is gone. I don't speak very well. I speak no Spanish unless I've had a bit of red wine. So for now, I'm going to give this talk in English. And I do have some translations, but if there is anything that isn't clear, please wave your hand and we'll ask Lara to translate. Firstly, thank you. Okay, bueno. So firstly, thank you so much to the organizers for inviting me and for organizing my stay here. I love Argentina. I've done quite a bit of work here with Alejandra Sosa at Coede, and with Celeste we co-supervised one of her PhD students, or she and Alejandro's students. And yeah, just always a pleasure to come back to this amazing country where all the things that I'm fighting against are indigenous and live happily amongst the other plants. So this is, as I said, I'm talking about a new way of dealing with these aquatic invasives from what we call a classical biological control approach to an augmentative biological approach. And the worst weed that we deal with is camalote, water hyacinth. It's the world's worst aquatic weed. And I always feel bad coming here to talk about these terrible plants from South America, but it's also good to see, or I don't know if it's good to see, but that there are efforts to try and contain these when they even are becoming problematic in their native range. So these are the majority of the plants that I work on, or that we work on throughout Africa. And you can see each one of those yellow dots is a record. A lot of those yellow dots are no longer there because we've had such successful control using biological control of these plants. And we're working on camalote, as I said, Salvinia molesta, Pistia stratiotes, which has recently become quite problematic here in Ibera and Corrientes, Chaco, and Myriophyllum aquaticum. And all of these species are also expanding their range further north with climate change. So they're going further north into Europe, into Asia, into the US, and so and further south in the southern hemisphere. And so we're still dealing with a lot of problems associated with these plants. And just to highlight one of the worst invasions that has ever been with water hyacinth, with camalote, is in Lake Victoria. And for those of you who don't know, it's in the middle of Africa. It's Africa's largest, greatest lake. It's certainly not the largest lake in the world. And it was invaded by camalote in the late 1980s, 1990s, and it rapidly spread and covered 20,000 hectares of the system. So a really huge invasion. And as far as the eye can see, it's water hyacinth across the system. And this is a system that is crucial to the livelihoods of the people who depend on this water body. They depend on it for transport, for catching fish, for all the ecosystem services that a healthy aquatic ecosystem delivers. And so this mat of hyacinth covering the system obviously has a huge impact on their livelihoods. And there you can just see a boat stuck in there. And as happens, the global north comes in and says, don't worry Africa, we'll save your problems, we'll donate funding, and we'll sort things out. And this is two harvesters that were donated by the United Kingdom. You can see they did a really, really excellent job. One of them even got the Prince of Wales Award for Innovation for the winner of the special category for environmental innovation, and that was in 1991. So this thing was donated, it was put on the system, and it pulled out water hyacinth every single day, and in 1998, that is what that system still lived with. So why do we have these problems outside of the native range, when in the native range, things like camelote co-occur with other aquatic vegetation? And I'm sitting in a room of limnologists, and you probably all know the reason why. But what we're dealing with is very altered systems in the invaded range. So that's one of the factors. And again, I'm sitting in a room of aquatic ecologists, of limnologists, and I just want to talk about why we're dealing with these huge issues in Africa, actually throughout the world. It's no matter where we go, the issues are pervasive. So we talk about bottom-up versus top-down food webs. Does everyone know about a food web, right? I mean, a food pyramid. So the big thing that I want to focus on is that we've got bottom-up processes that are driven by the amount of primary producers in the system, the green stuff, the plants, the phytoplankton, the blue-green algae, and they in turn, their abundance is driven by the amount of limiting resources in the system. And what are we talking about? We're talking about nutrients, mainly light, obviously water. And depending on what your limiting resources are, determines how much green is in the system. And that then influences what eats the green stuff, the herbivores, which influences the primary carnivores, which influences the secondary carnivores. Then the other way would be the top-down, and it's not that they're mutually exclusive, they work in combination with each other. And so in this case, we're talking about top-down control from predators that control the herbivores, that control the amount of green stuff in the system, sort of independent of what's going on with those limiting resources. And what's happening throughout the world is that resources in these aquatic ecosystems have become abundant. They are no longer limiting. So nitrogen and phosphorus are entering our systems at a rapid rate, and that is increasing this amount of green stuff in the systems. And in South Africa, municipalities, the treatment of sewage, I don't know what sewage is in Spanish, but I hope you all know what I'm talking about. So it's one article a couple years ago said a tsunami of human waste inundates our rivers and dams. And there's 97% of the municipalities in South Africa do not treat the water to the water quality guidelines that government sets. And so all that sewage, everything that we are flushing down our toilets, is ending up in the rivers, or the majority. In addition, a lot of that sewage isn't even getting to the wastewater treatment systems. There's so many leaks along the way that we're getting raw sewage going straight into our water bodies. And then on top of that, we've got increasing urbanization, industrialization, agriculture, all fertilizing crops, animal waste, it's all going into our water systems. And as a result, we've got this increase in nutrients, this increase in resources, and so an explosion of plants, an explosion of algae, and so it's having huge impacts on our system. So we talk about these bottom-up processes, and as a biocontrol science, I'm coming in from the top-down side of things, where if we put enough if we increase the top-down pressure from the herbivores on these plants, in the face of these abundant resources, can we get it down to some sort of sustainable control? So for those of you who aren't aware or aren't au fait with biological control, as biocontrol scientists, we work on species that come from somewhere and are introduced somewhere else in the absence of their natural enemies. So in the absence of the herbivores that normally keep them under control in their native range. And we can talk about any kind of herbivore. Do capybaras, do carpincho eat wood hyacinth? Okay, I would never use that as a biocontrol agent because it doesn't only feed on that plant. What we look for as biocontrol scientists is the insects and the mites that are host-specific or monophagous, that feed on those plants, and also some pathogens, things like fungi, that only target those plants. And what we do is we find these natural enemies, which is why I get to come to South America quite frequently, and we introduce them to the invaded range. It goes through a very, very strict process. We're not just, oh, look at this cute thing, let's release it. It goes into quarantine. We do years of testing to ensure that they are monophagous, that they only feed on the target plant that we want to control. They don't target any economic plants, nothing indigenous, nothing in the native biodiversity. And then we also have to make sure that they are damaging. There's no point in introducing something that's not going to have any impact on the plant. And so once we've satisfied all those conditions, we can then apply to the government for a release application. They review the document. If they have questions or concerns, it'll come back to us. We'll address those concerns, and then eventually we get permission to release the agent. And this is a similar thing in the US. It's a similar thing in Australia, in New Zealand, throughout Africa. And it's just not a thing in Europe. Europe is very, what's the word? Risk averse. They're very happy to release biocontrol agents against agricultural pests that are not host specific. But if you talk about an environmental problem and releasing a biocontrol agent, it's, oh no, that's way too scary. And so the advantages of weed biological control is that it's environmentally friendly. We're not putting huge blankets of glyphosate onto a water body. So there's no pollution. There's a low risk of non-target effects. There have never been unanticipated host shifts. So we've never seen a weed biocontrol agent move onto a plant that we didn't expect it to move onto. They're self-sustaining, cost-effective. When they're out there, they multiply if conditions are right. And it's permanent, so these weeds can't escape their natural enemies. Once those biocontrol agents are out there, there's going to be that top-down control on the plant. And that's just a picture of a little weevil for Pistia stratiotes. That's Neohydronymus affinis, and I think it's one of my favorite little insects. So we've released biocontrol against a number of these floating aquatic macrophytes throughout South Africa, throughout Africa, and we've had a lot of amazing successes. And one of them is with Azolla folliculoides, which is throughout the province, well, throughout Argentina. And just to go back, those tracks on this system, it's a small little system close to the university where I work. Those are big water monitor lizards that are walking on top of the Azolla because it is so thick. And in this system is a tiny little fish, only known from this river, Sandelia benzii. It's a little minnow, and it disappeared from the system because of the impact of this aquatic plant. And in the 1990s, a tiny weevil that is found here throughout Argentina, throughout Brazil, was released, and very shortly that system was returned to a functioning aquatic ecosystem. And the best news was that this fish came back. So it was obviously in the system somewhere, and it's now got a really good population growing in this small little system. There's bigger systems, nice before and after. You have to show these. You have to show how wonderful it is. Salvinia molesta, again, widespread throughout South America. We released a weevil, Certivega salviniae, and again, beautiful before, after. And I just wanted to put this in. It's Kenya in the Masai Mara. So a lot of the work has been done through the 1980s, 1990s, but we're still working with these insects. We can still send them north into African countries where these plants are a huge problem. This was May 2022 in the Masai Mara. Anyone watch any nature shows, you'll know how important the Masai Mara is to savanna ecology. This system was covered in Pistia. We released Neohydronomus. That was in May, December, so 7 months later, the system was clear. So depending on the weed, Camalote is not that weed, but depending on the weed, we can get very fast control that is sustainable and long-term. Okay, so we go back to Lake Victoria. We go back to 1998, where this lake is just covered in this plant. People have given up fishing. They've had to go into towns and cities to earn money another way because there's the fish aren't there anymore. And in the 96, 97, scientists from Argentina, from Fuede, from the CSIR in Australia, from the USDA in the US, and from South Africa, started releasing a biocontrol agent for water hyacinth that was collected by Ugo Cordo and Perkins and a whole bunch of Argentine scientists. These weevils were released onto the lake, but not only was it we're from the Northern Hemisphere, or we're from wealthy countries, we're going to show you what to do. People who lived around the lake were shown how to rear these insects themselves and how to put them onto the system and take responsibility for the infestation on their lake shores. And so here you can see, this is actually Malawi, so we did it at, well, not we, them, the guys before us, they did it on Lake Victoria, they did it at Lake Malawi, and those are the two weevils, well that is the one, two weevils, Neocatana bruci, Neocatana acornia. They've been released throughout the world against Camalote and are the mainstay of water hyacinth biological control. You can see in that bottom picture there, the small larvae burrow down the stems and go into the crown of the plant and really destroy it, and then the plant sinks. And so this started in about 96, 97. By 1999, more than 90% of the water hyacinth on Lake Victoria had disappeared. And the biocontrol scientists patted themselves on the back and said, we've done an amazing job. And then some other scientists came along and they said, why did water hyacinth vanish and is it going to come back? And they said that it was not because of biological control, but it was because of a reduction in photosynthetic active radiation. So light that plants need to photosynthesize. And yeah, this is 1996 to 2001. Between over 1997, there was an El Nino event, and there was a lot of cloud cover. And these scientists said that water hyacinth decreased because it couldn't photosynthesize. And the biocontrol scientists said that's absolute nonsense. The water hyacinth disappeared because of biological control. So the decline of water hyacinth was due to biocontrol by Neocotina. And this was the data that was presented in the paper. So it's cover hectares of water hyacinth, so up to 20,000 over time. These arrows are when the main release events of these weevils were. So they said water hyacinth really started to increase in 96. By 1999 it reached its maximum and it collapsed because it was the result of these insects building up and crashing. Now we're all scientists here. Do you believe the story? I mean, I believe it. But there's not enough data here to show that. They never measured anything over that time. There was no access to Sentinel satellites. There was no funding to go and spend every week on Lake Victoria. And so absolutely no fundamental data was collected for this entire project. And then those guys came back again and said, was it caused by climate or biocontrol? The reply, and once again they said, if you have a look, every time your plants decline is when that photosynthetic active radiation was at its lowest. Anyway, there was this argument. The biocontrol scientists couldn't prove it, and those guys were adamant that it wasn't biocontrol for whatever reason. And so we have to, as biocontrol scientists, we really have to ensure that we collect the right data. Correlation does not imply causation. And it was a very hard lesson to learn. And so now we collect data. We collect environmental data. We collect biodiversity data. We collect plant population data, the biocontrol agent population data, the economic data. Whatever it is, we are collecting data. And that's what I really want to show you today. And that's my colleague Dave Kinsler, who's usually the guy behind the computer doing all the cloud computing and the Sentinel stuff. But every now and then I get to throw him into a very polluted system and make him collect some data. And over the years, we have collected a lot of data. We've shown for biodiversity, we've shown what the negative impact of these mats of invasive aquatic weeds are on aquatic ecology. We've done a lot of work on macroinvertebrates. I've seen a couple talks today already on macroinvertebrates. They're wonderful. They're excellent indicators of the quality, the health of the ecosystem, the quality of the ecosystem. And we can really show with nice before and afters that by using biological control, we can increase or return that biodiversity of those systems to a functioning state. We've worked on Pistia, we've worked on Aconia or Pontidaria, Camelote, Salvinia. We've worked on them all, and we're collecting really nice data to show the benefits of biological control. We've also done the economics. Aquatic invasive macrophytes cost governments millions. Ask the US, Florida, Louisiana, Mississippi, those southern states spend an absolute fortune. I'm talking hundreds of millions of dollars annually in herbicides and in mechanical removal. In South Africa, we don't have quite as much dollars as the US has, but we do, in the past, we have spent a lot. And what this paper shows, Mary Maluleke, who is an amazing, she was an economics student, but really wanted to be in the environmental side of things. And she had a look at what the benefit-cost ratio was of biological control versus herbicidal control. And she looked at 3 different types of herbicide control, so controlling the plants from a boat, controlling the boat, we call it a bucky, it's a truck, a small truck, or a knapsack sprayer where you wear the knapsack and walk around and spray it. And the benefits, she did 2 different scenarios, but it's 90-1. Okay, the benefits of biocontrol are 90 times greater than spraying the plants from a boat, 165 times greater than spraying the plants from a truck, I don't know if that's 1,000 but it's a lot. So the benefits, the economic benefits are huge. And then you also think, well, what about the benefits of not putting those herbicides into the system? Those aren't even measured. With all the attention on glyphosate and cancer at the moment, and we're still putting it into our ecosystems like it's absolutely fine. So if we look at water hyacinth, all those other 4 species I've shown you there, we can get really good biological control relatively quickly. But water hyacinth remains a challenge. It's the world's worst weed. And in South Africa, we released 8 different species of biocontrol agents against this plant, and that's more than any other country in the world. And there's a couple of reasons for it. So this is a picture of some plants. You can see they're heavily damaged. There's quite a lot of herbivory on there. This is probably from 5 different biocontrol agents, and you'd expect the plant to be impacted by this. But no, they thrive. All these insects are on there, and these plants just grow, and they just grow and just grow. Why? Those limiting resources are not limiting. The water's eutrophic. It doesn't matter how much damage those herbivores are putting on the plant. They've got an endless supply of nitrates and phosphates, and so they just keep growing. Another thing is that we bring these insects from, and I showed Brazil here because it's warmer and more tropical than we are right now. You bring these insects from low altitude, warm climates where they've evolved in very humid tropical areas and in slow moving systems, and we introduce them into high altitude, much colder sites, and that impacts their physiology. So it takes a lot longer for them to build up their populations. If there's a frost event, they reach their thermal limits, they're impacted. If it gets really cold, they can die. So this cold weather really affects how well biological control does, particularly in our high altitude cold sites. So Johannesburg, where I live and where there's a lot of water hyacinth, is 1,800 meters above sea level, and it gets really, really cold in winter, and so that's a very big impact. And you can see here with a bunch of authors, Rodrigo sitting here in the room, climate mismatch between introduced biocontrol agents and the invasive host plants. We really need to understand how to improve this mismatch so that we select the right agents that can actually do well in their new environment. So in 2013, despite knowing all of this, we released another agent. And what made us think that it was going to do any better than all those agents already released? And we didn't know, but we did it anyway, with the rationale that added pressure might just suppress the plants even more. This little delphacid, Megamellus crutellaris, comes courtesy of Argentina. Rodrigo, I'm looking at Alejandro. Alejandro Sosa did all the research, the initial research on this insect. Incredible, you'll see it's an incredible biocontrol agent. And so bringing this agent across from Argentina to other countries in the world is really helping to improve aquatic ecosystems. This is the first system that we released it at. It's a system near Grahamstown, near Rhodes University, where I was. And beautiful green water hyacinth in the summer. We released Megamellus there, and look at that. Do you think that's Megamellus? No, that's cold. That's frost damage. And so, again, we released this insect into the same conditions and expected it to do well. But what we did do was record a lot of data. So we released it in 2013, and then in 2017, I had a PhD student come and work with me. We saw Megamellus in the field, it was there. It wasn't doing that much. And he went out and did monthly sampling for 18 months. And he did various measures. He measured how tall the plant was, measured how long the roots were, how many leaves, how many daughter plants. And he also counted the number of megamelis per meter squared. And this is the biomass of water hyacinth over this time. So May, we've got the same seasons as you. Whenever you're European talk, we have to try and flip it. So he started in May, started in winter. This is what the biomass was, fairly low. By January, it reached its peak. So midsummer, it's doing exactly what we expect. Megamelis at the same time. He found some at the end of autumn, and then very little. And we didn't release it again. And then it started to increase. And as it started to increase, we got the classic decrease in water hyacinth. And so it then increased. Water hyacinth had decreased, which then implied a crash for the herbivore. So no food. The plant crashed because of herbivory. The herbivore crashed because of no food. And what we realized is that it takes a very long time for the biocontrol agents, for megamelis, to catch up with the plant. So water hyacinth can get going very quickly as soon as it starts to get warm, but it takes much longer time for megamelis to build up a decent enough population, and then it crashes. And then it's winter, and then we have to start again. So if you have a look there, what we realized, what we have to do is get this peak of megamelis, which is in April, so just before winter. We actually need that peak to come at the beginning of the season, so right at the beginning of the season. And we then took this to the systems. So this is Johannesburg up here, very cold, high up, very polluted, most urbanized area. The water bodies are full of nitrates and phosphates, and there's a lot of water hyacinth. So all these we also don't have natural lakes. We have impoundments, and so we've slowed down the water flow. We've created perfect environments for these weeds, so slow water flow, lots of nutrients, the plants explode. And here, this is a dam called Hardebeespoort. It's a 2,000 hectare dam, it's just north of Johannesburg. And it's had water hyacinth on it since the 1960s. And the government controlled it with chemicals, all kinds of chemicals, for a really, really long time, up until, and especially during the 1980s. But whenever they stopped spraying, water hyacinth would come back. So it was just this constant, water hyacinth grows, spray with chemicals. And that's what the water looks like. It's South Africa's, some argue, Africa's most polluted system. The houses around this place are some of the most expensive in the country. People don't actually understand how dirty or how polluted the water is, until of course it turns bright green. And in the 1990s, all the available agents that were in South Africa at the time were released. And they were there, but they couldn't do much, because as soon as their populations built up, they were either knocked back by winter or by herbicides. So in 2018, we were asked to please step in and develop a biocontrol program. And we said, absolutely not. It's never going to work. It's cold, it's polluted, and it's just a political nightmare. But they said, sorry. When I say they, the government said, no, you have to get involved. And so we went and inspected the plants, and look at that. This was before we released megamelis. The biocontrol agents, in the absence of herbicide, I forgot to mention, they stopped spraying the system in 2017 because they said, why are we spending money on herbicide when there's no more water hyacinth? And then what happened? The water hyacinth came back. And within a year, we got to that really, to like, I think it was about 40% cover on the system. But the biocontrol agents built up as well. And so here we're dealing with these abundant resources, few herbivores, classical biological control, And what we wanted to do was change that to inundative biological control or augmented biological control, which involved frequent inundative releases of the plant hopper. So when I say frequent, every week, inundative, between 6,000 and 10,000 hoppers a week. How did we do that? We set up a farm. We set up a mass rearing station where we employ people living with disabilities. So this is Landile and Majeke, and they suffered with polio as kids, and so they're disabled, never had a job before. And this program that we call the Sisonke program, which means we work together, provides this team with a job opportunity. They get health insurance, they get a pension, and they're creating, they're working in meaningful jobs, solving environmental problems. So there you can see them collecting the insects with small aspirators. We package them up into takeaway food containers and literally put them in the post. We send them to my PhD student. We set up a small rearing station at the dam at a school, and this is how we started this mass rearing. And this is what the dam looked like in September, so that's early spring. So this is now after the cold winter. There's 35% cover on that system. In December, later that year, it had gone down to 20%. But the plants were still very green. And Megamelis, you don't notice the damage until the plants are actually about to drop dead. So we were like, okay, we can use this cool app that's been developed. We can have a look at what's happening. But then in January, I had a field trip and I went to go check what was going on. And that's the dam wall. And someone said they've sprayed. There's been an illegal spray. Someone saw an aeroplane and they've put glyphosate out over the whole dam. And we said, nonsense, this is Megamelis. And how did we know? Well, there were a few things. Firstly, the green is other plants growing on top of water hyacinth, on top of the dying water hyacinth. So it was using it as a substrate. And if there'd been herbicide, those plants would have died as well. Secondly, we found outbreak levels of not only Megamelis, but also the neocotyma weevils that had been there since the 90s and were now given the opportunity to build up. And by the end of January, that water hyacinth had gone down to 5%. This is the peak of summer. This is the hottest time of the year when the water hyacinth should be at its maximum. And then when obviously winter came along, this was COVID. This was when Paula Garvazoni was stuck in lockdown with me in my house. And we could still monitor what was going on the system over winter because we had these sentinel maps. And then we started seeing more green. And these plants come back from seeds. So Kamalote produces thousands of seeds per plant, per flower, and they remain dormant in the seed bank. They remain in the sediment for up to 25 years. And what we found in a previous study was an average of 2,500 seeds per meter squared. So we got rid of that layer of water hyacinth. Come springtime, there's nutrients, there's light, because there's no water hyacinth, and we got seedlings. So we got this germination. And by the end of the year, we were back up to 42% cover. And as a biocontrol scientist, you had patted yourself on the back and you're like, oh. But we carried on releasing. We set up more rearing stations. So we created really good stakeholder relationships with communities living around the dam. We got them to start rearing the insects very much in the same way as the scientists had done in the 1990s around Lake Victoria and Lake Malawi. And the bugs exploded again. And in February, it was down to 17%. The plant plants were in such poor condition that the insects, these are the neocotina weevils, they just abandoned the plants because there was no nutrition left in them. Megamelis abandoned the plants because there was no nutrition left in them. That's a tennis court at one of the estates, and that's just Megamelis flying around the lights. In the morning, that's what the caretaker had to deal with. We got people complaining that they couldn't eat their pizzas at the restaurants at night. We love our barbecuing, our parrillades, our braais, and people couldn't sit outside. And we had never seen anything like this before, and we had to say, listen, these insects are not going to attack anything else. They're not harmful to you, they can't bite you, but everyone's an entomophobe. We're terrified of insects and these things flying around. And anyway, there were newspaper articles, but we had to say it's a good sign that the plants are dying. And by March, we were down to 7% again. This is the Coves is the housing estate where that tennis court was. So 25th of March, that was the last remaining patch of the water hyacinth. You can see how brown it is. By the beginning of May, not a single plant left on the system. And what we realized is that by going from classical, where you just throw out some insects and hope they do their job, to augmented control, so increasing that top-down pressure, even in the face of abundant resources, we can get good control of these aquatic plants. And just to show you the bigger picture, we've done this now. I haven't got 2025 on there, but this is cover. We've also got monthly measurements of all those other things. We've got insect numbers, we've got plant numbers, you name it, we have all the data. And what we're seeing is every single year, after that end of summer crash or midsummer crash, nothing over winter, every September we're getting these seeds germinating. The amazing thing though is that the biocontrol agents don't allow the plants to flower. So there's no flowering, so no new seeds are going back into the system. So does that mean we're gradually going to get fewer and fewer plants coming back? We'll see now. It's July, so we've got about a month or two, and maybe we're going to have another explosion, or maybe a lot of those seeds have already germinated and we're wiping them out. So we'll see. We've got each year that we get the data, we're like, okay, we need to publish it. No, one more year. No, we need to publish it. No, one more year. So we've got 2025. I don't know. I think we should publish it. And we set up, as I said, all these community rearing stations, and without them we definitely wouldn't have been able to get as many insects onto the system as if it had just been coming from Rhodes University alone. And what we've shown is that by fostering an engagement with the community, they understand that, yes, government should be doing this, but while government is trying to sort things out, take things into your own hands. And so we've shown that these 10 community rearing stations have really contributed to a community of practice of getting water hyacinth under biological control. We got a lot of press. This is a local South African paper. The Times in the UK wrote a thing about it. And I didn't translate this one, I apologize. I didn't know where to put it because I wanted to show you the team. So even though we know that water hyacinth biocontrol is limited by eutrophication, by cold winters, by herbicide, by hydrology, by these huge seed banks, if we adopt an inundative mass release strategy, we can get control of these plants. What's really important is we need stakeholders, and the work that Ale is doing around San Vicente down in Buenos Aires province is exactly that, getting the community to understand what their role is. And then it also offers incredible training and employment for people who would have never had those opportunities in the past. And so what we are doing now is taking this technology to the rest of the world. And this is a picture of a rearing station in Zimbabwe. I was telling colleagues that Megamelis has exploded in this rearing station, but they have no money for petrol, for gas, so they can't get these insects out into the field. So really trying to kind of overcome all these different obstacles is huge. Where's Martin? How much time do I have? Can I give another quick example? Because this was going to be the end. But then I thought, let's go from South Africa to Cameroon, where I can highlight the work that Rodrigo Diaz and his team did, using this inundative release strategy. Okay, so this is Cameroon, and there is a lot of water in the country, and it comes down here to this lake called Lake, well, it doesn't come down, but here we are, this Lake Ossa. It's kind of near the sea. It's a very multiple branched lake, and it's big. It's 4,500 hectares, so it's a significant size. And it's home to the African manatee. And we'll go, oh, because they're really cute and charismatic, and maybe not as cute as Kapincho, but they're pretty cute. And in 2016, this lake got covered by Sylvania molesta from one end to the other. And the local people called it Boko Haram, and if you know anything about African politics, they're a terrorist group, or they called it Satan 2, El Diablo, dos. And there's just pictures of the extent. And again, this is a system where people are reliant on this water body for their livelihoods, for fishing, for transport. And here you can see groups of people trying to manage the plant. And then I can't even remember the order of events, but between us, we got contacted by AMCO, which is the African and Marine Mammal Conservation Organization, between us and Rodrigo, and they wanted Certavegas. The Certavegas that we misreared in South Africa had got a algal parasite, and so we didn't want to now send this parasite out. And Rodrigo stepped up to the plate, and with his mass rearing team, with his team of students and researchers, they initiated this incredible biocontrol program at this lake. And recent publication of optimizing aquatic weed management in Lake Ossa, harnessing the power of biocontrol and real-time satellite monitoring. And PAR, very low photosynthetic active radiation, is a result of cloud cover. And if you know anything about the tropics and rainforests, there's always a lot of cloud cover. And using those sentinel images is really difficult through clouds, but Dave Kinsler, who's the magic man, developed an app where he can use radar and calculate the amount of these plants even through cloud cover. So July 2021, we're looking at 50% of the system covered in Sylvania molesta. AMCO, LSU, Center for Biocontrol, collaborative program, got these weevils sent to Cameroon, where they were reared and released, and in 2 years it went from 50% cover down to 17% cover. All this, I'm sure if you know Sylvania molesta, when it's not looking very good, it goes quite brown. These green islands are a grass, Echinocloa pyramidalis, that again uses the plant as a substrate, and then when it gets heavy enough and the Sylvania is rotten enough, it flips over and sinks. And this also happened on Lake Victoria. And through this this radar imaging could calculate the cover of Sylvania over time. So from January 2019 through to 2023, here you can see how it increased and then decreased. These bars are actual measurements of the composition of the amount of plant on the system. So at 800 hectares, it was 100% Sylvania minima. At 1,400 hectares, it was 97% Salvinia, and it was made up of a little bit of mixed indicynochlora. And then as the biocontrol increased its effect and the plant started to die, we got less and less Salvinia being predominant, down to this point, which was the sort of middle of 2023, where there was only a bit of mixed Salvinia with echinochlora and echinochlora. But I think the most exciting thing about this project, because I didn't mention that this manatee disappeared, which is why AMCO got involved in the first place, the African Marine Mammal Conservation Organization. They couldn't find this manatee. It completely disappeared from the system, which was its main breeding ground. Hey, Rodrigo, it was like the main, one of the main places for African manatees. So this weed came in and took over, and it disappeared. And they had, they put in acoustic monitoring devices, couldn't pick anything up for quite a while, and then that popped up. Any guesses? You're thinking it. It's manatee poop. Manatee poop. So that was the first sign that manatees had returned to the system following the biological control of Salvinia melissa. And I know it's a big, charismatic, endangered species, but that return to a system meant so much. It was so symbolic for the people and for AMCO, and that the functioning of this aquatic ecosystem had returned to some kind of normality. And that's the kind of work that we can do throughout Africa. We can take it into India, into China. It's being used here in Argentina. Rodrigo is using Megamelis now in the US, and so we really can get sustainable control, long-term control, using nature-based solutions in our aquatic ecosystems. And that's where I'll end up.
Hola. Thank you very much, Julie. Very nice. ¿Tenemos tiempo para alguna preguntita? Pueden ser español, inglés, traducimos, hacemos lo que podemos.
Okay, thank you very much, Julie, for your very interesting talk. I have a question. You show pictures of the lakes covered by tons of macrophytes. Then the macrophytes disappear. What happened below the water surface? Because I imagine a lot of organic matter decomposing and consuming oxygen. Do you have any information on that?
I do, and that's a really great question, and I get asked that frequently. So that system is very, very polluted. And there's been a mass balance study of the phosphates coming into the system and what the water hyacinth takes up. And I can't think of the mass balance numbers now, but it takes up 0.1% of the phosphorus that's actually entering. So it's negligible. There is carbon-based biomass there. If it was sprayed, that biomass would rot and sink, and we'd get anaerobic decomposition. There'd be hydrogen sulfide and general smells and stuff. Biocontrol is a much slower process, so you're not getting this sudden drop. You're getting it's gradual, and it is that biomass is sinking. It's not adding nutrients to the system. It's adding carbon for sure. And in the absence of biocontrol, those plants turn over all the time. So they're constantly putting that into the system. So we're slowing it down, and we're reducing the amount that's going in. Of course, ideally might be to remove it as it's dying, but on that scale, it's just not possible.
Yeah, thank you very much. It was very nice. I was wondering, especially in South Africa, I know that when Eichhornia disappears, cyanobacteria are coming. Are you working in the alternation between weeds and cyanobacteria?
So, again, one of the main questions that people ask, if the water hyacinth goes away, are we going to get cyanobacteria? And in those years when water hyacinth was chemically controlled, there would be, who's got a green, like your jersey, and that lake would turn green, and the sludge from the algal blooms was thick. Kids were getting sick, you name it. There's a lot of work on allelopathy and how water hyacinth is allelopathic and outcompetes the cyanobacteria. And I don't have data, but what we've seen over the last 5 years, there hasn't been a single cyanobacteria outbreak. My hypothesis is that because the water hyacinth is still in the system, those allelochemicals are still there, keeping the cyanobacteria at bay. But what I didn't show you was that another plant came in place of it, and it was Salvinia minima. So it's all about the nutrients. If we can control the nutrients, we'll get better control of the plants. You get rid of one thing, you're getting another. So at the moment, it's not cyanobacteria, but it is another invasive macrophyte.
¿Alguna pregunta más? Puede ser en castellano y... ¿Cómo es tu nombre? Lara traduce.
Yo tengo una pregunta, voy a hablar en castellano, perdón. También, de lo que pude entender, capaz lo dijiste y yo me escapó. ¿Hay alguna otra consecuencia? Vos están sembrando, yo la verdad que de insectos poco y nada, están sembrando estos bichitos para que se coman las macrófitas. ¿Hay algún otro impacto en la fauna, flora del resto, y no sea solamente del lago y de las macrófitas del lago, que ustedes estén como analizando, teniendo en cuenta, pensando? Porque es como una explosión de estos megalón y capaz que afectan a otra parte del ecosistema, y no sé, eso me preocupa.
It's a really long question.
But it was easy. She was wondering if there is another impact that you are analyzing instead of what?
All of ecosystem,
Not only the
water,
yeah.
crops.
Yeah, and again, another question that I always get answered. And I was chatting with Rodrigo, why do I keep calling you Rodrigo? Because Rodrigo's sitting next to you. I'm going to IMAPI conference next month. I'm going to give this talk. And they're going to ask that question because they're all invasion biologists. And they're going to say, you're working on water hyacinth, but all that megamelis, what impact is that having on the ecosystem? Is that what you're asking? Yeah, I don't know. But it's a really important question. It's temporary, so it's not going to be a permanent fixture. Those explosions have only happened twice. Once in 2021, and again this year. It happens for about a week, 1 week of explosion, then the water hyacinth disappears. But surely it must have knock-on effect. Is it increasing predator populations? Spiders, frogs, birds? I'm sure it is. But again, it will be temporary. But how knock-on is temporary? So it's a really important question, and it is something that I think we as biocontrol scientists have to get better at. And I've got a proposal for a PhD student to look at the dynamics of the fauna associated with water hyacinth over a year. So when there's very little megamelis, what's in there? As megamelis increases, what's coming in? When it explodes, what's happening? So yes, it is a very good question.
How was the experience with the outreaching and everything? Do you have to be like really? You have to train the people. I mean, like not the scientific community, like the non-academic community. Did you have to teach them? They were like easy to.
The first thing to do is to break down that ivory tower that we're scientists and we're very clever and this is very difficult work, and say this is easy and anyone can do it. we try and relate it to farming. If you keep healthy plants, if you keep the plants happy, you'll keep the insects happy. We run small training workshops at the beginning of each, well actually now we'll be running one, just to get the teams back on. We also do this for other invasive species, and so each species has to be tailor-made requirements. And we have WhatsApp groups. We frequently communicating. People will send pictures, and we just had a huge frost in one of our huge measuring centres, and all the water hyacinths just frosted over, and the megamelas crashed, and yeah, everyone was like, "What are we going to do? It's okay, we've still got time. Let's heat it out. Let's wait." So yeah, it's constant communication. It's being encouraging. It's doing all the things that, telling you you're doing a great job. People get cross, like, why are we putting our money in when government should be doing this? And changing that narrative to, okay, well, I see I can do something and make a difference. I think, yeah, when people take ownership and it's easy enough it's an easy technology, it will be taken up very, very easily. Yeah.
¿Alguna preguntita breve que os ha quedado? Ricardo.
Many thanks for your presentation. I wonder, regarding the question before about the implications in the ecosystem, and you talked before about the testing you made before releasing biological control species. So, are those testing including some of these trophic or non-trophic interactions with the ecosystem, or just the testing deal strictly with the trophic interaction with native plants or this exotic plant?
Yeah, these are great questions. So the testing in quarantine usually is limited to the host specificity. Is it going to impact native plants, economic plants? How's it going to impact the target plant? We do look at we're looking more and more at food webs and trophic dynamics, and looking at, well, if we're releasing a delphacid into a system and there's other delphacids, will it acquire parasitoids? If it acquires parasitoids, is that then going to spill over into the native population? So it's kind of been done. I don't know, Rodrigo or Ale, if you've come across more than what we do. We do look in the native range, so in what's going on in the field here, and try and correlate it to what might happen in the introduced range. But as far that usually comes after the release.
So you don't usually compare the associated fauna, like in the native and
No, we do. We definitely do. But once it's in the invaded range and we've released it, we then do post-release evaluations. And that then is when we quantify any of these types of insects. Like, for example, gall-forming biocontrol agents that might then provide habitat for other species to occupy. Those are things that you can't test for in quarantine, but it might have an effect later on.
So the impacts after this release you looked for weren't to be concerned up to now?
No, there've been one or two things, like I can think of the what's that little flycatcher in the Sierra Nevada? Tamarix, which is an invasive plant, and a little endangered flycatcher. I think, is it in New Mexico or in New Mexico in the US? And this little endangered flycatcher has now found habitat in this stand of invasive plant, and its numbers have just increased beautifully. there's a biocontrol program now wanting to be implemented, but the ornithologists or the conservationists are saying, but if you take away this invasive plant, then the flycatcher is going to disappear. So yeah, it becomes what's that? There was an old woman who swallowed a fly. I don't know why she swallowed a fly. Do you know that? She swallowed a spider to eat the fly. She swallowed a bird to eat the spider to eat the fly. Anyway, she died in the end. So yeah, we don't. I think that's where biocontrol needs to focus more. We know that the science itself and the controlling the plants is fine, but I think getting into the next stages prior to release might be important. But then we also say you've got to weigh up the cost benefit. You know, if you've got 2,000 hectares covered, and then you get a bit of a apparent competition between something and something. I think as long as things don't go extinct, don't quote me on that. I don't know if you want to add anything.
Hablo porque, bueno, trabajé mucho justo con el insecto. En el caso de Megamelus, por ejemplo, se trabajó mucho, no directamente probándolo, pero sí considerando potenciales interacciones en los ambientes donde se introducía, donde se reconocía que otro tipo de delfácidos, como dice Julie, había en los nuevos ambientes y qué tipo de interacciones tenían con parasitismo, predación, etc. En general a nivel de insectos, que es lo que más trabajamos.
Bueno, muchas gracias. Thank you very much. Julie, is there a question for you?